Welcome back, grade 10s. Today's lesson will be the final lesson on electromagnetic radiation, and it is also the final lesson on waves in general. So it's the final lesson of this topic. Now, in this lesson, we're going to talk about how sometimes electromagnetic radiation behaves like a particle, not just like a wave. We're also then going to move on to some past paper questions for revision. So let's start understanding electromagnetic radiation as a photon. In 1905, Albert Einstein proposed that electromagnetic radiation has a dual nature, meaning that it has a double nature, where it can behave as a wave and it can behave as a particle. So up until then, it was generally accepted that electromagnetic radiation is made up of a wave called a light wave. But now we understand that sometimes electromagnetic radiation behaves like a particle. Now, particles and waves are two fundamental concepts in physics, and they mean very different things. Because when it comes to particles, particles are localized entities. They have a definite position in space. Waves, on the other hand, are spread out over space. They don't have a definite position because waves are just the movement of energy. Now, what led Einstein to propose this dual nature of electromagnetic radiation is something known as the photoelectric effect. And what that means is that when certain wavelengths of light are shone onto a metal surface, electrons are then emitted from that surface. What that means is that certain wavelengths of light, and when we talk about certain wavelengths of light, we are referring to light that has a higher frequency and a higher energy. So when these higher energy light waves are shone onto a metal surface, electrons are emitted or rejected from the surface. And that's because the electrons absorb that energy and then they have enough energy to jump off the surface. Now, that would not apply if this was a wave rather than a particle, because a wave would result in an accumulation of energy on the surface until eventually electrons would jump off the surface. But in this photoelectric effect, Einstein observed that certain frequencies, lower energy frequencies, you can shine them for a very long time and they will never emit electrons. You can also increase the intensity of that lower energy light and it will never eject an electron from the surface. Whereas certain frequency lights that have higher frequency and higher energy, regardless of how intense that beam is, will immediately emit electrons from the surface of the object. And so that means that there is a certain amount of energy in these higher frequency light waves that allow the electrons to absorb that energy and immediately jump off the surface. So the electrons are not emitted based on the intensity of the light, but rather based on the frequency of the light. So you can take a very low energy light and provide a very high intensity, but the electrons will not be emitted. Or you can take a very high frequency light, and even at the lowest intensity, it will eject electrons. So, for example, red light has low frequency relative to violet light. Red light cannot emit electrons from the surface of a metal. It doesn't matter how long I shine it for. It doesn't matter how intense that red light is. It doesn't matter how much red light I'm shining at the metal surface. It will never eject electrons. But violet light does emit electrons from the surface of a metal, regardless of the intensity of that light. Now, this effect could not be explained by the wave theory of light. According to the wave theory, the electrons should be emitted based on the intensity of the wave, meaning that a wave with a higher intensity would allow energy to build up over time and would eventually emit electrons. But that is not the case. So therefore, Einstein proposed that light is composed of tiny particles, which he called photons. Let's define a photon. This is a very important definition in your syllabus. A photon is a particle that is associated with electromagnetic radiation that carries energy in discrete or isolated packets. And what that means is that photons are particles of electromagnetic radiation. And different photons will carry with them different amounts or different packets of energy. So the energy in a photon of violet electromagnetic radiation would be higher than the energy of a photon in red electromagnetic radiation. When photons strike a metal surface, they transfer their energy to the electrons, and that's what causes the electrons to jump off the surface. The photons of red light are just not high enough in energy to ever emit electrons, while the photons of violet light have high enough energy to emit electrons from the surface of the metal. Since Einstein's proposal, there have been several other experiments that have provided evidence for this particle-like behavior of light, such as the double slit experiment. And if you'd like, you can look up on YouTube the double slit experiment. It is a fascinating experiment that indicates the particle wave duality of light. Our current evidence supports this concept of wave-particle duality of electromagnetic radiation. What is the relationship between the energy and the frequency of a photon? Well, the two of them are directly proportional. So a photon that has a higher energy has a higher frequency. Or a photon with a higher frequency will also carry a higher energy. We may calculate the energy of a photon as E equals h times F. Now, we can see that E and F, because they're on the same line, are directly proportional. H is Planck's constant. It is a constant value provided to you on the formula sheet of 6.6 times 10 to the minus 34 joule seconds. Again, this is a constant. So if you have the frequency of a photon measured in hertz, you can calculate the energy of that photon measured in joules. And we can see that the relationship is directly proportional because if the frequency is greater, then the energy will also be greater. Now, recall that when it comes to electromagnetic radiation, all electromagnetic waves have the same speed, represented by c rather than v, because it is a constant of 3 times 10 to the 8 meters per second. Now, the frequency of a wave may be calculated as the wave speed divided by the wavelength of that wave, and in the case of electromagnetic radiation, that wave speed is a constant through air and through vacuum. Our original formula was E is equal to H times F. And what we're doing now is, in place of F, we are inserting speed divided by wavelength. And so we may also derive this formula for the energy of a photon, where, again, H is Planck's constant, c is the speed of light, which is also a constant. Wavelength is measured in meters, and energy is measured in joules. What that means is that given the frequency of a wave, we can measure the energy of a wave by using this formula over here, or given the wavelength of a wave, we can also measure the energy of a wave given this formula over here. And both of those formulas, as well as these two constants, are given to you on a formula sheet. So let's look at some examples of how we calculate the energy of a photon. Calculate the energy of a photon of green light that has a frequency of 6 times 10 to the 14 Hertz. It is a very simple formula. The energy is equal to Planck's constant times frequency. So it's 6.6 times 10 to the minus 34 multiplied by the frequency of a photon of green light. And that means that a photon of green light has this energy associated with it. A photon of ultraviolet light carries 4.95 times 10 to the minus 19 joules of energy. Calculate the wavelength of ultraviolet light and provide your final answer in nanometers. So we were asked to calculate wavelength. So that is measured in meters, and our answer would automatically be in meters, but then we need to convert our final answer into nanometers. This formula over here takes into account the energy and the wavelength. Now I've rearranged this formula to calculate the wavelength. The formula is given to you like this on the formula sheet, and you don't need to rearrange it. You can just start plugging in values and then rearrange the numbers as you go along. However, I rearranged my formula up front, so the wavelength is equal to Planck's constant times the constant speed of light divided by the energy associated with ultraviolet light given to us in the question. So that 6.6 times 10 to the minus 34 times 3 times 10 to the 8 divided by 4.95 times 10 to the minus 19, and that gives us a final answer of 4 times 10 to the minus 7 meters. However, the answer should be provided in nanometers. Now, we already did a lesson on how to do conversions. When we're going from a bigger unit of measurement to a smaller unit of measurement, we need to multiply. And nano is associated with 10 to the 9. So it's 4 times 10 to the minus 7 times 10 to the 9 nanometers, which equates to 4 times 10 to the 2, or simply 400 nanometers. Some electromagnetic waves are listed below: UV, infrared, radio, X-rays, and gamma rays. How are electromagnetic waves generated? Now, this question gets asked regularly on past papers. What you want to say, if it is out of 1 mark, you simply want to say accelerating charged particles. But if it is out of 2 or 3 marks, then you also need to add in a bit more information. Now, this is not a definition, so you can use your own words. But what we want to explain is that charged particles in motion, or accelerating particles that are charged, create an electric field. And a moving electric field creates a magnetic field. And a moving magnetic field creates an electric field. And they travel perpendicularly to one another. But generally speaking, all you're asked to state is that electromagnetic waves are generated through accelerating charged particles. From the list above, write down the waves that are used in a TV remote control. Now, if you recall from our last lesson, we learned that we use infrared in TV remote controls. Used to sterilize instruments in a hospital, and we learned that both UV rays and gamma rays are used for sterilization. Have the greatest penetrating ability. So, of the different electromagnetic radiation types given to you on the list, the one with the greatest penetrating ability is the gamma ray. Used in the detection of cancer would be either X-rays or gamma rays, and used in the treatment of cancer would also be either X-rays or gamma rays. Ultrasound is used to obtain an image of a fetus. Explain why X-rays cannot be used for that purpose. Now, this is a commonly asked question, and you need to understand that ultrasound is a sound wave, and it wouldn't be damaging to the fetus, whereas X-rays are a type of electromagnetic radiation with high energy that can do damage to DNA. So what we need to say is that X-rays are a high energy electromagnetic wave that can penetrate the body and cause DNA damage, increasing the risk of cancer. An X-ray photon incident on a body has a wavelength of 2.1 times 10 to the minus 9 meters. How much energy does the photon impart on the body? Now, an incident photon or an incident ray means it is the wave, the light wave or the photon that hits the body. Other light waves would then get reflected off the body. So we get the incident ray, which hits the body, and the reflected ray, which gets reflected off a body. So what we're saying here is that an X-ray photon hits a body with this wavelength, and we want to calculate the energy that this photon contains, and therefore when it hits the body, it imparts or gives that energy to the body. This is our formula. The energy is H times C divided by the wavelength. H and C are both constants, and we divide that by the wavelength in meters of the X-ray photon. And we get an answer of 9.43 times 10 to the minus 17 joules. The table below lists different types of electromagnetic radiation and their relative frequencies. So here we can see the different types of electromagnetic radiation and their frequency ranges in hertz. Now, when we answer questions given information in a table, we want to answer the questions based on the information given in the table. Write down 3 properties that are unique to electromagnetic waves. So, what are some properties that are unique to electromagnetic waves relative to other waves? Well, firstly, electromagnetic waves are the only waves that can travel through vacuum. Electromagnetic waves have a constant speed in vacuum and in air of 3 times 10 to the 8 meters per second. Electromagnetic waves originate at the sun as accelerating charged particles from chemical reactions that take place at the sun. Based on the data in the table, which radiation has the highest energy? Explain. Let's go back to the table. Now, what we know is that frequency and energy are directly proportional. Gamma rays, we know, have the highest frequency and the highest energy. So the answer here would be gamma rays, because based on the data in the table, it has the highest frequency. So if you said, well, gamma rays have the shortest wavelength or gamma rays have the highest energy, it's not wrong, but you're not answering the question based on the data in the table. A certain electromagnetic wave has an energy of 1.99 times 10 to the minus 20 joules. Identify the type of electromagnetic radiation associated with this energy. Now, we were given the energy of this electromagnetic radiation, and we're asked to figure out the type of electromagnetic radiation. Now, the table gives us different types of electromagnetic radiation, and it gives us their frequencies. So for this question, we would need to figure out the frequency of this electromagnetic wave, and then go back to the table and identify the type of electromagnetic radiation that it is associated to. So I've rearranged E equals H times F. I've rearranged it as F equals E over H. We were given the energy in joules, and we're dividing that by Planck's constant, and that gives us a frequency of 3 times 10 to the 13 hertz. Now we have to go back to our table and identify the electromagnetic radiation that's associated with 10 to the 13 hertz, and that is infrared radiation. Consider the laser pointer and the cell phone below. What type of electromagnetic radiation is associated with the laser pointer? Well, we learned that that is visible light. And what type of electromagnetic radiation is associated with the cell phone? And again, we learned that that is microwave radiation or radio wave radiation. A laser pointer uses red light photons with a wavelength of 620 nanometers. What is a photon? This is a definition. It is particles associated with electromagnetic radiation that carry energy in discrete or isolated packets. Calculate the energy associated with a red light photon. Now, we were given the wavelength, but we were given the wavelength in nanometers, and we must convert that into meters. So when we're going from a smaller unit of measurement to a bigger unit of measurement, we have to divide, which is the same as saying times 10 to the minus 9. So we would either divide by 10 to the 9, or we would multiply by 10 to the minus 9 to get to meters. Now we need to work out the energy based on this wavelength. H and C are constants, and we get a final answer of 3.19 times 10 to the minus 19 joules. Why is it dangerous to light a laser pointer in a person's eye? This is also quite a commonly asked question, so I made sure to include it here. And what you want to mention is that if the light focuses on a small spot in the retina, especially the central part of the retina, it can cause thermal damage and potential loss of vision. That brings us to the end of the section on electromagnetic radiation and waves in general.